So in this video, I'm going to explain what is meant by norm and what is meant by dual norm. So say we have a vector x which has n components, and the p norm for x is going to be this, which we call as LP norm, and the expression for this is that. And the dual norm for this would be this, which is LQ norm, where 1 by p plus 1 by q is equal to 1. So this is a universal relation that relates norm of a vector and its dual norm. So we can easily find out what is the dual norm of a vector using this formula. And another formula is this thing. So this is more intuitive or physical formula for finding out the dual norm. Say for x, if p is its norm, then the dual norm would be this expression, which is argmax of x transpose d, where d is less than or equal 1. Now, what does it actually mean? So this thing is basically a dot product. So, and this means the projection of vector x in the direction of another vector d. So we want argmax of this whole thing means we want the maximum projection of x in the direction of d. In the direction of d. Now, d is limited by this constraint. D is less than or equal 1. So we'll have to find out a certain d for which value the projection of x will be maximum. So basically, this is an optimization problem where we are finding out an optimal d for which this value is going to be maximum. And this value is basically this maximum value is probably is basically, so this is actually not correct. This is gonna be actually max values such that d is less than or equal 1. So that is gonna be our dual norm. All right. And how can we find out d? So d is a vector and it has different component. It has say, if it's a set of a number of components, then each component is determined by using this expression where di is equal to sine of zi multiplied by absolute value of zi to the power q minus 1 over the norm where the power is q minus 1 and it's basically L norm. It's the LQ norm. All right, when we have this definition, after that this becomes more clear if we see an example that is for 2 norm. So when we put, so in this equation, if we put p equal to 2, then we get this. So if p is equal to 2, it becomes, instead of p norm, it becomes 2 norm. So 2 norm. So, and this equation becomes this equation where x 2 norm for of x is gonna be x1 square plus x2 square plus dot plus xn square to the power 1 by 2, which is nothing but distance. So 2 norm basically represents distance, and the dual norm for 2 norm is going to be this, which is actually the true norm itself, because 1 by p plus 1, this equation 1 by p plus 1 by q is equal to 1. If we put p is equal to 2, we also get q is equal to 2. So which means the dual norm of a true norm is actually itself. Now, for a more physical understanding of this, we can use this expression. Now again, this is wrong. This is gonna be max and such that. So we want to maximize the projection of this distance. So this is a vector basically. So x is nothing but as a vector. This is x. So if I basically draw this, so somewhere say this is x, right? And then we have d. Let's use a different color. So we have a vector d, and the angle between them is theta. So we have so this is xt. So here what we want is to maximize this. So this dot product, we want to maximize this. So how can we maximize this? We need to find out what value of d maximizes this whole thing. So the projection of x should be maximum when the value of d is maximum. Now our constraint is d is less than or equal to 1. Now the maximum value of d for true norm is actually 1. So what does it mean? It means d is equal to this thing, x by x over true norm of x. So when d is equal to 1, we have this. Now y, let's see from here. So for maximum projection, y d is equal to 1. So for our condition, this constant, we have d is less than or equal 1. Now in 2D, so in 2D we have two components of d, and this becomes root over d square, d1 square plus d2 square is less than or equal 1. And if we square this up, we get d1 square plus d2 square is less than or equal to 1, which is nothing but a circle. Similarly, in 3D, there will be three components, d1, d2, and d3, and this will become a sphere. And in n dimension, it's going to be d1 square plus d2 square plus dn square is less than or is equal 1, which is nothing but a unit ball, an n-dimensional unit ball. So what does it mean? It means that we are creating something somewhere like a ball where it's uniform and it's symmetric. So it means that we can select a point on this this ball, on top of this ball, say this one, let's use this thing, on this ball where d is equal to 1, and this is going to be the maximum value of d. So for maximizing this thing, we need to maximize d, which is nothing but 1. And this happens when the angle, when this happens, then the angle between this one and this one is nothing but 0. So in that case, when this d is equal to 1, we have maximum projection, and we have d equal to x over true norm of x. This actually directly comes from this equation, where we know that D has multiple values. So here, like in this circle that we can see, so this is a, here we have actually a set of D. So D can be from 0 to 1, any value. So we could choose any value. So less than D less than or equal 1, we could choose any value, but we have chosen 1. So the value of D could vary from 0 to 1. That means this all entities can be expressed in terms of I. So Di is like one component or one instant of D. And the formula for Di is sine Ci, absolute value of C. So here it's gonna be for our two norm thing, it's gonna be Di is equal to sine of Zi, and this is gonna be what, Zi, and so because our Q is 2, it's gonna be actually 1, and then this is gonna be Zi 2 1. So we can just remove this one thing, and so here if I do case by case analysis, if I do the case by case analysis here, what does this become? So say case 1, when say Zi is greater than 0, then the sign of Zi equal to plus, and because Zi is greater than 0, then absolute value of Zi is gonna be Zi. So if we put these values here, this is gonna be Di equal Ci over Zi over Z 2 norm of C. So case 2, say Ci is less than 0, and it means sine of Zi is gonna be negative, and also Zi is gonna be minus. So sorry, this is Zi minus Zi. So if we put these values, we again get Di is equal to Zi by Z2. So for all cases, this relation holds where D when D is equal to 1, D is equal to actually X by Zi. So that's why we can put this value here, and if we put this value, we can just rearrange to bring this together, and this thing becomes this, and from here we can get this. So it means that the dual norm of a two norm is the two norm itself, and it also let us know that it also it also provides us an intuitive sense that say when we have xt in this direction, as I was showing, is xt, and when D is also in the same direction, then we have the maximum projection, which is basically the maximum projection of because D is in the same direction of xt, and it's basically a unit vector. So the maximum projection of xt would be basically itself. So this makes a very intuitive sense. But now it's really important to understand the property of this constant D is less than or equal 1. Right now it's a circle or sphere or unit ball which is extremely symmetric, and then like it becomes very intuitive that x2 star is gonna be x2. But if this is like the value of p is different, this relation doesn't hold. For example, say if we if we consider p is equal to p is equal to 6, then what does it become? It becomes 1 by p plus 1 by q is equal to 1. So 1 by 6 plus 1 by q equal to 1, which means q is equal to what? Q is equal to 1 by 6, 5. 1 by q is equal to 1 minus 1 by 6 equal to 5 by 6. So q equal to nothing but 6 by 5. So if p is equal to 6, q is not is equal to 6. Q is different. So p is not is equal to q. Unlike this 2 norm where p, the two norm for this case, where p is equal to q. There is an intuitive sense for that, and that can be brought directly from this relation where we can apply this. So if we have x 6 star equal max of d is less than or equal 1, such that we have to maximize xt of t. Now here this condition is no more symmetric, because the equation for this one, we know that sine of zi and so this is zi q minus 1 over q norm of q minus 1, right? So if we put the values here, so sine of zi and zi of, this is gonna be q is 6 by 5, so 6 by 5 minus 1 is 1 by 5, 1 over 5. And then we also have this thing, which is c 6 by 5, and this is 1 over 5. So which becomes like quite complex equation. This thing is quite complex equation. So this is not symmetric. That's why we cannot confidently say that we can like for the 2 norm we could choose d equal to 1 and make it like pretty intuitive case, but for this one it doesn't work that way. And finally, if we solve it, we will eventually get that say 6 norm of x is gonna this is actually gonna be x 6 by 5. So this is not the same as the 2 norm where x 2 star equal to the 2 norm itself. This is different. And this is all because of this condition, because this is not a symmetric unit ball like the 2 norm. It's a different, it has a very different geometry. So similarly, as we change the value of p, the constraint, this constraint starts to have very different geometries, and based on this geometry, the relation between the norm of a vector and the dual norm of that vector changes.